Hello, hello. I'm so happy today to have Evan White, the director at Biosinatic Labs. And Evan, I'm so happy to have you here and looking forward to learning from you. But I'm going to start at the very beginning. What does Biosinatic mean and why that name?
Yeah, thank you so much, Ved, for the opportunity to speak with you and talk a little bit about compostable materials and also this term biosynthetic. What does that even mean? It's a marketing term that we made up. We fabricated that term to separate us from the field of other biodegradable materials, and there's some challenges associated with basically getting around the greenwashing of the word biodegradable. So that separated us out in the field and allowed us to position ourselves as an analytical lab to help industry partners also develop such materials. So the term also carries with it more than just marketing. We like to describe materials as biosynthetic. Um, that have a good end of life outcome for their desired purpose. So for compostable materials, ultimately that's following the standards, but making sure the microorganisms will digest those materials into CO2 and water and biomass and ensure that there's no nefarious persistent plastics left behind. So we do a little bit of a deeper dive into microplastics and persistent materials from even the biodegradable materials. So the term biosynthetic is basically a term that describes biology, of course, for bio, and then synium is the end life stage of life of organisms. But in the context of materials, we basically put those two words together to describe the end life stage of materials. So that's where the word comes from in its Latin roots.
Interesting. I want to know more about cynium. I've never heard that term. It may be my ignorance, but what is when you say that it is the term for end of life?
Mm-hmm.
Tell me more about it. What does cynium? How does that term relate to end of life?
Yeah, so I'll preface first with I'm a chemist, not a biologist by training. So I study polymer chemistry,
Nature is
but
full of chemistry, Evan.
at the end of the day, yeah, the cynium is my understanding is the end stage of any life form. It's like what their the organization of their biology. So you can think of it in terms of like a mayfly might be that last day they're in flight to reproduce, but for us it may be different, and for a tree it's probably quite different as well. And for these materials that we're making, we consider their end of life the receiving environment. Hopefully compost, industrial compost, managed environments. But if it is mismanaged and winds up in soil, then we need to design for that end of life as well, or the ocean. And that tends to be where mismanaged plastic winds up, right? Soil or the ocean. So that's the end of life we need to design for.
Super. Now I'm going to step back into you, Evan White, and you're growing up. Clearly, you've had some influences that have led you to this strong belief in doing something really impactful. And I see that you've grown up mostly in Georgia, it seems, by your bio. Tell me more about your growing up years, and were there specific kind of incidences when when a light bulb went on and you said, this is what I'm going to do in life?
Yeah, so you're right that I'm a Georgian. I've grown up here my whole life, and now I'm working in Georgia as well. So I have a pretty good pulse on the state, and I grew up outside of Atlanta. So I'm a product of the suburbs and growing up in single family home kind of living situations. And that's actually how most Americans grow up. That's 55 to 60% of Americans live in more or less the suburbs, some type of dwelling like that. And I saw growing up, the expansion of Metro Atlanta, the loss of habitat, and the production of litter. That comes with society, and it's not unique to Georgians or Americans. It's any and all developed societies will produce some amount of garbage, and litter is part of that story. And we can do our best to collect it and manage it, but there's always going to be some level of leakage, and it's usually not something that's front and center in terms of what people want to address. It's icky and stinky, and no one wants to deal with the issue. They don't want to. They want to put it in the trash can at the end of the curb and not think about it every week. But I see it as I'm an environmentalist by I think by design. So I see solving the garbage problem as a way to solve some of the problems in our environment and support cleaner environments and ecosystems.
Yeah, when I compare it to my growing up, I grew up in India, and
Hmm.
when you're in a place like India, you see a lot of litter around you. Here in US, the garbage guy comes and takes it away. So my getting into something like the area of compostable packaging is a little more obvious, right? I'm seeing it all the time. I'm like, okay, this is in a water body. This is on the side of the road. This is, wherever you kind of, there's huge garbage dumps. But it's not so visible where you grew up. So why is it that it still kind of attracted you enough to say that I'm going to make this my life path?
Uh, I still think you're right. Is less visible here for sure, but it's still visible for those who are observant, and you can see it in any national park you walk in. And I having hikes with my father a long time ago, we would always try to bring out more garbage than we bring in, and we'd always bring a packed lunch with us, and that was like a mission. It's like try to find some garbage, and it was always easy. Usually, you get your one or two pieces within the first kilometer of your hike, but that's the principle of that strategy is to make the place that you are visiting cleaner than when you arrive there for the first time. So I think it's about leaving the places that you live in a better environment, in a better place than when you arrive.
Sorry, and why biochemical engineering? Like that's a very specific direction in terms of learning and then doing your PhD as well. So
Mm-hmm.
what attracted you to that path?
Yeah, when it comes to I guess the marriage of biology and chemistry, it's really the understanding of how biology deconstructs the chemistry we make. So I'm a polymer chemist, so I like to design how polymers are organized and what the monomers and the polymer backbone looks like is important for how biology will or will not deconstruct that polymer backbone. So it's really that understanding of what nature likes to do with the things that we make as chemists, especially in environments like compost or soil or microbially rich environments that you want to see those materials break down and ultimately turn back into the base monomer for life, which is carbon dioxide.
And is this something that you wanted to do for a while? Like I'm deconstructing,
I see.
the process of how you got to biochemical engineering. Sure, you're a polymer chemist, but that's a choice, right? That I'm going to choose this area of learning amongst many others. So what made you go in the direction of polymers and then eventually biochemical? Was there a reason that kind of instigated this direction?
Yeah, I mean, ultimately, it comes down to understanding how things work. I always like to dissect old TVs and VCRs and electronics because you kind of get into the nuts and bolts of what makes that device function. And it's the same with chemistry. It's just the bits and pieces are not electrical components; they're molecules and parts of polymers. Especially in material science, where it's not just a single chemistry makes up a plastic. It's a mixture of lots of chemistries and understanding how each one of those little components makes up a given property or gives rise to a flexible film that can be extruded on a 48-inch web. That's amazing. Why does that happen? And how do you design something that is better for the environment with those understandings about how all those little bits and pieces work?
Yep, makes sense.
Yeah, still an engineer at the end of the day.
Yeah, it's just breaking down different kind of products
Yeah.
and putting them together. So I also see this interjection in your life. The University of Georgia created this new materials institute in 2017, and again Bioseniatic lab also comes around similar kind of time. Was there any relationship how those two kind of grew together? And I would love to learn about the New Materials Institute and what they are doing as well.
Yeah, yeah. So let me kind of back up and describe kind of the relationship between the Bioseniatic Lab and the Institute. So the Bioseniatic Lab is housed in the New Materials Institute. The institute itself is I don't know, few dozen faculty and staff from different departments across campus, chemistry, engineering. I'm part of veterinary medicine and other disciplines and other departments as well from the university. And the institute ultimately was created to design materials and interfaces that will provide solutions for single-use packaging. Other formats of recycling we've kind of explored a little bit, but really our big focus has been around compostable materials for single-use packaging. Um, you can think about where recycling might make sense for larger formats, but you kind of get to this mass barrier where if the packaging doesn't weigh enough, it's not like techno-economically feasible to recycle. You can always recycle anything, but at what cost? And we wanted to focus on the problematic packaging formats, which are typically the lightweight, complex materials that have multiple chemistries. Multi-layer packaging has been a big focus of the work that I've been studying because of its multiple chemistries and its challenges to recycle or upcycle, or depending on who you ask, downcycle. But ultimately, there's not a straightforward recycling feature for those formats, unless you can make the entire packaging compostable. But that takes a lot of evidence to support the claim, especially since these packaging formats can have well over 10 chemistries in them.
And when we look at the New Material Institute, so are there many such companies like your lab that are working in the direction of compostable packaging, or is it a more widespread kind of materials institute?
Uh, it's more so widespread. I can speak to the compostable side and the testing side of what we do here. Uh, we also do some projects around infrastructure as well. In 2024, last year, uh, I ran a program with the Institute in conjunction and funding from the Walmart Foundation to run an infrastructure curbside collection compost pilot program for 400 households and design basically an awareness campaign and ultimately a cost structure for the city to do curbside collection for organics in the city of Athens. And that's not really material science; it's infrastructure development. And so we like to not just think about how do we make new things, but how do we deal with the new things we make. And so we also work on the back end with infrastructure too. I've done some that project we did in conjunction with Jenna Jembeck, and she is basically a recycling expert in the space. Anything, any assessment of a city when it comes to the infrastructure for recycling or composting, like her team at the Circular Informatics Lab basically did those assessments for us on that project. So, looking at a city level, what is the inputs for recycling or compostables? What do the waste stream look like for packaging, and what does the management look like both for recycling and for compostables? Because they kind of play off of each other in terms of waste management. You could argue the same thing for landfill management too.
Yeah, no, absolutely. So you've used two terms, and I want to dig in a little deeper because you understand plastics really well, and
Mm-hmm.
you use the term recycling. Is it
Mm-hmm.
really possible to recycle plastic? And when we say recycling, it fundamentally means you break down something and recreate the same thing. So I want to challenge
Yeah.
you a little bit there, or it's not even a challenge. I want to get into the nuance of it,
Right.
especially for listeners. That is that even possible to take a film and make another film from it? Just
Right. Right. There's
by breaking it down.
it's challenging is the short answer, but the reason for that is a thermodynamic challenge. And these polymers want to oxidize after you process them over and over and over again. And that oxidation leads to deterioration of properties, but more importantly, to the formation of chemistries that are nefarious for food contact. So it's basically you have to have a clean enough resin to support direct food contact or even secondary food contact for the packaging. And after you've recycled a polymer several dozen times, it breaks down into its base components. It oxidizes, into other oxidized smaller molecules that might taste bad, might be have toxic effects at certain concentrations. So there's a limit to how many times you can process those over and over and over again. Um, and the case is true for polyethylene, for polyolefins. It's true for polystyrene and for polyesters as well. And that's in part because of the contamination. You just can't get the recycling stream and I literally mean 100% pure, 99.95s, to get to the purity needed for very clean recycling without all these side reactions happening. But ultimately, again, I'm not a recycling expert. But in terms of compostable packaging, that's what we study, and we're ensuring that those materials are fully compostable, which has the same requirement for purity. That's all the organic carbon is converted into CO2. So you have to have a sufficient amount of carbon, 90% really by the standards, be converted into CO2 to claim for compostability. And I guess you could say the same thing about recyclability. How recyclable is something depends on the infrastructure, right? But if you look at the material itself, glass and metals are infinitely recyclable, but none of the plastics are, none of the polymers are. Ultimately, they will oxidize, they will break down, and that's just the fundamental nature of these polymers. Now, if they are broken down enzymatically, biologically into CO2, that's the base monomer of life, and that can be rebuilt back into celluloses and back into polyesters. So, that's the type of recycling we want to study is, true organics recycling, cycling carbon through the Krebs cycle, make sure that carbon is metabolically active. And some of the tools we have here can help prove whether these new materials are in fact compostable. And that's really what people want with the compostable material, is that the implication is that microorganisms are metabolizing that carbon. That's what the average consumer they may not be able to articulate that, but that's the expectation, is that bacteria, fungus, it's going to eat that plastic and it's going to go away.
I'm going to keep you. I know you said already
Mm-hmm.
that you're not a recycling expert, but you are a materials expert. So I'm going to keep you
Sure.
there a little bit to dumb it down for me and maybe some of the others who may be listening. Is like, let's simplify it. Say let's take a simple polyethylene based plastic bottle, like a water bottle.
Mm-hmm.
And what we are told as consumers is that, oh, this is very easily recyclable, right? So somebody throws it away and it goes to a recycling facility. Does it typically mean that it'll become a bottle again? And if it does, let's assume that it does. Is there a certain number of times that it can become a bottle, and then it becomes something else? It's broken down into something else. How would that typically look like from your kind of exposure, that,
Mm-hmm.
this is what really happens? A plastic bottle is thrown
Yeah.
away thinking that this is going to become recycling fundamentally means it becomes a bottle again. But I presume, like you said last time, that when you were speaking, was that ultimately it has to oxidize. So what happens then? How many times, and what happens ultimately? What is the material it becomes?
Yeah, that's all great questions, and I'm sure they could be answered in several different ways. But when it comes to how many times, it depends on the purity, and really it depends on purity. And those impurities give rise to breaking apart the polymer backbone, and then you get what's called a reduction in the molecular weight. So the overall size of the molecules gets smaller, and that what happens is that gives rise to material properties that are not favorable in processing. So you have a molten polymer that requires a certain viscosity. It needs a certain melt strength, so that even though it's molten, it has a certain elasticity. Those properties will be influenced deleteriously by degradation after you've processed it several times, several heat cycles. And you've seen this probably. You've seen clues of this before in a lot of packaging. You'll say made with X% recycled content. It's usually not 100%, and there's a reason for that, and that's because of the material properties. They're not favorable. They decrease with time, and we can put other chemistries in there, chain extenders and other like post polymerization modification agents to do reactive extrusion and other strategies to extend the life of that recycled material, maybe one or two more times, so that you can include more recycled content, especially for things like RPET, recycled polyethylene terephthalate. But at the end of the day, you're not going to be able to process that 100 times over again, which you would be able to do with something like aluminum or steel or glass. Um, so, ultimately, and those materials will oxidize too, and they have their recycling challenges. But when it comes to the organic polymers, they have a limit in terms of exposure to time and temperature to oxidation. So their properties will not be very good if you recycle a bottle 50 times.
No, that's great. That's great. So what I'm typically told, and this is where the question was actually coming from, that typically a water bottle will be made into a fiber that will become polyester, and
Mhm.
then there is no more kind of it'll lie in the Atacama Desert catching fire. And the second part of that question is ultimately there has to be an out, right? So as consumers, what happens is that we are told it's recyclable, and like you said, it may be one, two, three, maybe six times, but then there is no out, right?
Mhm.
I presume in an aluminum, like you gave an example, ultimately it will demineralize and it can probably go back to soil. In glass, I don't know again if it's crushed, then it probably is again silica. In paper, of course, it becomes cellulose, so it's again going to degrade. So what would happen in this case? Is there an out eventually, or it's just a microparticle when you say that it'll break down? What happens?
I don't know the out. You've got me stumped. I'm not sure what the out is for these materials, and our societies don't know either. We put them in landfills and dumps, so that's the out.
Or you burn it?
or we burn it. Yeah, yeah. Especially in Europe. Uh,
Yeah,
but
yeah, and
but
then you try and catch those gases.
mhm. Right, exactly. So for the incumbent materials, I'm not sure what the out is, and that's actually a big one of the big challenges of the Ellen MacArthur Foundation's circular economy.
Yeah.
For materials, like what are we going to do about circular materials? Energy has its own suite of problems that could be solved, but for materials, once we use them one time, they're done, and that's why we got to think about not just oil based but also bio based. And sometimes the terms oil based and bio based get thrown around with compostable, but I think I should clarify. But compostable materials are agnostic as to whether or not they're made out of oil or bio based carbon, and ultimately compostable materials will turn into CO2 if they're truly compostable, CO2 and water. Uh, but the microorganisms don't care if that plastic or that polymer was made from oil. You could make cellulose from oil, and those organisms would degrade cellulose just the same as they would natural bio-based cellulose. So it's important to think about bio-based versus petroleum-based, and we should try to make materials bio-based. But if I have to weigh which is a bigger issue, whether bio-based or it needs to be compostable, I think the waste litter issue is a bigger issue right now. But we're going to have to eventually solve the materials issue too. We're going to have to make everything out of bio-based solutions eventually.
And I'm going to have you expand on that because that's an important point that you've made. Educate us more on the fossil fuel based materials. So you're right. You can make a PBAT or a PBS and it'll compost. And you can make a non compostable substance from a bio based material too. So how big a challenge do you think? And I understand your point of view that the current challenge is more compostable, but the future challenge, as you said, may be a fossil fuel issue. Because the other challenge, one is, of course, the availability of fossil fuel has to be ultimately limited at some point. But the other challenge, and this is where I want to understand from you, how big a challenge is the amount of carbon utilized in order to create fossil fuel based polymers? So, of course, it's a
Mm-hmm.
side stream. But that said, even to kind of create a material like a polyethylene, I'm sure there's a lot of trapped energy there. So, one is the source itself. in terms of fossil fuels, and the
Hmm.
second is the process. And how do you see that?
Yeah, so you're kind of touching a little bit on life cycle analysis for like the making of materials and the embedded energy and materials to produce things. Uh, I know of this as an issue, and I know of some examples. I don't study this personally, but I'll give an example of PLA versus polyethylene. That's a common example. How much energy is required to make a kilogram of PLA versus a kilogram of polyethylene? It's I don't know that number, but I think the economics can point to some insights into that number. I don't think it's a direct comparison, but usually the cost is an association of energy, and higher the cost, the more energy and or the more materials it takes to make it. So, and also you have to think about what it's coming from. So, lactide is made from corn ultimately, and that's competing with food supplies for human and animal consumption, whereas ethylene is a waste product of transportation, fuel refining. So like one's a waste product, ethylene gas, and the other is a commodity that could be fed to animals or to humans. So the cost structure is going to change, and the life cycle analysis changes based on that. But I can't give you a number for which is better. But I do know that PLA costs more, and I think energy and materials are associated with that higher cost. There's probably supply chain and all these other, you know, economy of scales and economics that I don't understand. But ultimately, I think you can look to the price in terms of energy costs to make materials.
I'm tending to
Yeah,
disagree.
for these commodity materials, I should say.
I'm
Yeah,
tending to disagree mainly because it may not be as direct as price.
right,
Because
right.
the challenge becomes that, like you said while you were speaking, one is a waste material
Hmm.
and one has got a fundamental cost, whether it's starch or vegetable oil or whatever you're using.
Right.
Because then we would say PHA is even more expensive or it has a higher life cycle cost, whereas you're actually using microbes to eat into something which is could be a waste. It could be even a methane gas
Hmm.
or something. So I don't know, but that's a good point. But
Yeah.
I would say it's also to do with where it is at life cycle. So the fossil based or petroleum based polymers have had a 70, 80-year run. There has been optimization that has happened significantly and scale that has happened.
Right. Right.
I don't know whether that is going to happen in case of PLA and PHA.
Hmm.
So I don't know. I'm just challenging the assumption that the cost may be directly proportional to the energy use. It may be also to do with the feed material, where it is on the life cycle, the scale of manufacturing, etc., etc.,
Yeah,
etc.
I agree with you on that. I mean, there's a huge history there in terms of traditional materials versus these newer ones as well. But yeah, at the end of the day, um, it's hard to get those numbers. It's hard to understand them fully.
Yeah, it's more complex, and of course,
Hmm.
the fossil fuel itself, and then if you looked at the trapped energy there, then it again becomes a different kind of challenge. But let's switch.
Sure.
There's a term that I saw, and it's a very interesting term: building stimuli responsive polymers. So, what does this whole idea of stimuli responsive mean, and why focus on that?
Yeah, yeah. So I guess that kind of goes back to my PhD work a long time ago. But I was making polymers that would change color in response to light. So they had these chromophores that were installed in the backbone called spiropyrans, and you shine light on them, they change color, which is great. But more importantly, they would change their charge state. So they would go from a hydrophobic, uncharged state to a Zwitter ion, and that makes it go from hydrophobic to hydrophilic. And we were looking at how polymers would reorganize differently if you take polymer blends or block copolymers with that special molecule, that special monomer, and see if we could get changes in phase separation or how polymers would organize on the nanoscopic level. So that's where that stimuli responsive uh, origin comes from, using light as a stimulus. But then, switching over in 2017 into new materials that are bio-based and compostable, the stimulus is no longer light. Now it's enzymes compost action, right? So now we're looking at how the stimulus has now switched from this photon into now we have a big bulky enzyme, and how do we design materials that enzymes can access and degrade? Because at the end of the day, those are the engines that are doing the degradation for compostable materials. So we're starting to get a little bit into some enzymatic studies. I'll publish some work on that this year, but ultimately the bacteria are the workers that are deconstructing the plastics that we're making.
I find that term very interesting when you said that you move from hydrophobic to hydrophilic. And again,
Mm-hmm.
my layperson understanding is that hydrophobic is something that basically tends to repel water,
That's
and
right.
hydrophilic is something that actually disperses water.
Yeah,
And how does that shift happen by the light stimulus?
yeah. So there's so you actually break a bond. So the molecule will absorb that energy from the photon, and it'll break a carbon oxygen bond that's kind of weak, and it'll break open what's called a lactam or a lactone. And when a ring opens, it makes this. It basically separates the charge, and now you go from this kind of hydrophobic molecule to a molecule that has two charge states separated, a positive and a negative charge on one molecule, and that's what's called really polar. So it becomes a water loving or water retracting molecule after that. What's cool and interesting about these spiropyrans is at room temperature they will eventually ring close and regenerate the hydrophobic state again, just at room temperature and ambient. You can accelerate it with temperature, but it's a regenerated process as well.
That's a full topic for another conversation, Evan. Now
Oh yeah,
I
that's a
won't, I won't bore
side
everybody with
topic,
it, but this is very
but
interesting.
it was
And
interesting.
as you were speaking, I was thinking of the lotus leaf, for
Hmm.
example. It kind of does
Yeah,
both, right?
yeah,
Because
that's kind of
because
what
you
we're
have
trying to
a
do.
waxy hydrophobic idea, and then you have the nodules that are more hydrophilic, and kind of it's
Hmm.
doing the both those effects to keep it clean. But I was intrigued by the idea that you could switch, that a stimulus would enable it to shift from hydrophobic to hydrophilic, and then you said back to hydrophobic. So
Yeah, yeah. What we're trying to actually do is we're making elastomers, so like kind of rubber band like materials, and they are block copolymers. So it's like you take something like plexiglass, polymethylmethacrylate, and then you attach butyl rubber to it in butyl acrylate, and then you get this kind of elastomeric material. You're taking a glassy polymer and attaching it to a liquidy, goopy polymer chemically, and you make these block copolymers. And what happens is you take that and you cast a film, and the polymers will organize on the nanoscopic level, and they'll do what's called nanophase separation. So basically, like dissolves like, just like in like general chemistry. It's the same is true with polyethylene and polypropylene and all the polymers. Very few polymers will dissolve in each other. Polyethylene will not dissolve into polypropylene. They're dissimilar enough, at least at certain concentrations. And that's what we were studying. Is you make these phase separated domains that are a certain organization, such that you get elastomers, and then you shine light on it. Can we change the elastomer properties by just the light as a stimulus? Turns out, not really. No, at least we couldn't measure it. But you could change how the films would organize if you were to make like cast films. But that was like some of my PhD work, and it sounds like a lot of PhD work. It just kind of goes into someone's thesis and
no, but it's always
gets
interesting.
buried.
And it reminds me, I don't know if you've come across this amazing kind of hero of mine, a guy from Hebrew University called Dr. Oded Shozayev. He has a wonderful TED talk as well. And he looked at collagens, mainly, and this is coming from your idea of elasticity. And he looked at growing collagens. So they injected tobacco plants with collagens and how they grew the collagens again for elasticity and then extracted them again.
Mm-hmm.
So it was super interesting, the work that they did, and made it quite practical and usable. And how do you kind of utilize that polymer and make it into substances and products and that kind of thing. And I do have a we did an early recording on the Good Garbage podcast with him, so you might want to have a listen. I think it's maybe episode 3 or something like that. That early.
Yeah, you've done a number of episodes. I got through a couple of them. I just got through your one with Eastman Kodak. But
Oh yeah,
yeah,
that's an interesting one too.
yeah.
But okay, let's move to the work that you're doing now at Bioseniatic Lab. What does that comprise of, and then what is the effort in terms of what are you trying to achieve by the work that you're doing at
Right, right.
BioSeniatic?
Thanks, Ved. Yeah, so the Bioseniatic Lab is basically our analytical workhorse lab for studying compostable materials. We run a lot of fee-for-service work and sponsor projects out of this lab, but ultimately it's a research and development space to study compostable materials, new materials, and to understand and design research experiments around understanding how new materials will or will not biodegrade. Uh, we have 252 bioreactors equipped with respirometers as our workhorse kind of analytical tool. Respirometers or respirometry is basically a process of measuring metabolism of that carbon source into CO2. So it's a biology experiment where we're just sniffing all the biogases coming off the inoculum is what we call it, the mixture of organisms that's doing work on compostable plastics. We have several other analytical tools that we use in conjunction with our respirometers to study compostable materials. We or at the end of the day, we're a fully equipped synthetic facility, so we can make polyesters up to several tens of kilograms, enough to do some field trials, and also to just fully characterize them, all the way from synthesis to end of life, which is the composting. And that's really where our team comes in at the Institute, is after we've developed, with guidance from our team, but developed materials that have the right polymer architecture, we put them to the tests and our respirometers and screen them for compostability. Um, we also do a lot of photography with that too. Like, I don't want to downplay some of the kind of the softer tools, because most everyone has this tool in their pocket. You can learn a lot from disintegration photography and mass loss experiments as well. The respirometry is a nice, kind of precise analytical tool for measuring gases, but you can learn a lot from just how samples physically break down over time. So we actually couple that a lot with photography. It helps paint a picture of what's like how your samples are actually breaking down, and it can garner some insights into strategies of how to make compostable materials break down faster, because that's what the end market, the composters, want. They don't want packaging that takes to the end of the standard to break down. They want something that will degrade as fast as possible. So that's the engineering balance, designing materials that are processable, cheap enough to be techno-economically viable, and when it gets to the composting process and that end market, it has to degrade in a reasonable timeline. And that reasonable timeline, it depends on where you are in the country. Here in North America, we have different climates in Florida than we do in the Northeast. So composting outcomes are slightly different. I know out west they do a lot of covered vessels, like gore cover composting operations. So it's a little bit different on the West Coast. But ultimately, composters want, if it's compostable packaging, it needs to degrade as fast as possible. We aim for about half the time of the standard. That's what we advise as a goalpost to aim for materials to fully mineralize, or if you get very, very close to complete breakdown by about 3 months in industrial composting, or about 6 months in home composting, if it can be designed that way.
And that's to do with the accelerated biodegradation at the lab, or the structure of the material that you're talking about in terms of the accelerating the degradation process.
It's the structure of the material, so it's how it's designed. Yeah. So there are strategies to design materials to degrade more quickly or more slowly as well. I mean, you can think about some environments where maybe you want an article to last 2 years and then fail, like in agriculture. You don't want to have your agricultural films falling apart in 2 months.
Yeah.
They wouldn't be very effective. So there's being able to understand the appropriate timeline for that use case, I think, is important. Um,
But
so
as the lab, are you also looking at uh, kind of collaborating in the material design side, or are you mainly focused on the degradation side, or is it both?
It's a great question, and it's both. So we do a lot of testing on the degradation side of that's what I call our fee for service work. It's that those kind of experiments are protective and with our clients, and insofar as all the IP stays with the client, like we're not going to do any other analytical outside of what we're told to, and just answer the questions: is it compostable, and then what timelines, and design some experiments around understanding that. So that's the fee for service work, and then on the sponsored project work, that's where we go down the rabbit hole a little bit deeper and look at applications and specific products that we want to design and see how we can develop new materials for those applications. So that's a little bit more challenging. That's the hard route. But we're more of a research and a development group than we are of a testing lab. So we're not ISO 17025 certified, which means we're not here to provide data to BPI or to Denserto for certification. We're here to develop new materials and help companies develop IP. That's what we're here to do. And once we have, kind of through testing and iteration, we've already have a candidate material that's going to be 100% chance of successful once you go to certification. So, and certification is expensive, and it costs a lot of time as well. So we want to, develop research projects that will de-risk that certification as well. So that's my little spiel about what we can do out of our lab. We have a couple of products or I guess technologies we're trying to commercialize into products. One of my pet projects is around a home compostable adhesive I've been developing with my collaborators here at the New Materials Institute, and we've designed it to degrade as fast as possible. 3 or 4 months in home compost to fully mineralize, because that's the layer that binds together other stuff, other slower to degrade architectures, polyesters in particular, and also cellulosics. And you need to separate those materials as fast as possible in the composting process. So you need to have glues that will degrade even faster than all the other materials. So that's why we've been focusing on home compostable adhesives. So we're going to try to commercialize that technology in 2025, and and you can think about some spaces where a home compostable adhesive might make sense, right?
No, absolutely. And I think people don't realize the complexity of adhesives many times, and then it creates a lot of havoc. But before we get into that part of it, I want to pick your brains on numerous material and names that we hear, and how do you see each one of them, and is there a certain preferred route that you have? So I'm going to name five, and you can add any
Sure.
more. PLA, PHA, PBS, PBAT, and PBA. So if you look at those five, how do you see the structure, and what is it? Like if you look at who would be the most worthy of these for you, or each of them plays a different role, but educate me on these materials that we hear of so often now.
Yeah, so those are all polyesters that you named. So those are all typically heat seal layers if we're talking about multi-layer packaging. But they also can be used like in agricultural films, like I touched on a little bit earlier. So depends on their application. But I like all those polyesters. They all make sense in different spaces, right? So PBS is a good one to point out because it's more affordable than some of the other polyesters, but it's only industrially compostable. So it won't degrade in soils or in low temperature compost, at least not in the time frames of the standards. So you can see where PBS maybe makes more sense for industrially compostable applications, and you could say the same thing with PLA. One that's missing, it's another material I like on that list I'd like to add is PBSA. So if you take a little bit of adipate and you pepper that into that PBSA polymer, it transitions it into a home compostable or soil degradable polyester. A little more expensive. Mitsubishi Chemical makes one of those resins, a resin grade that is PBSA called BioPBS, and we use it in a lot of our applications. works great to be home compostable too. So yeah, for all these polyesters, it makes sense. If the cost makes sense, then go for the home compostable option. You can say the same thing about PHA. Um, but yeah, at the end of the day, it depends on the receiving environment and end of life. If you're looking at a packaging format that say will be contained in a play space or a cafeteria or some place where you have control over inputs and outputs of packaging, think about arenas or football, soccer, basketball games. Those are op- great opportunities for PLA and for PBS type packaging, or even if it's some other mixture of these materials that really requires the industrial compostable condition, then that they probably would be a good option for you because if you're trying to consider which polyester to use, because if you're just getting into sustainability and you're looking at the different types of polyesters, it can be overwhelming. There's a lot of them, and trying to identify what works for what environment. Um, think about what your consumers are going to do with your packaging and what's the end fate for the particular article. Um, so that's my little piece about all those polyesters you just brought up. But I will say that polyesters aren't the only part of the story. There's also polyurethanes. There's also cellulosics and modified cellulosics. So it's that's just one class of materials that we have access to in our toolbox.
So I've spent two visits now I'm probably Daniel Caraway, and he's been on the
Yes.
show as well, RWDC. And again, I've learned a lot from him and the great work RWDC is doing. And what is your hope for the PHA? Again, the PHA range of compounds, because again, you can have
Right.
different molecular chains and you can have the PHBs and PHBVs and all of that. How do you see that evolving? Because Daniel is, of course, putting his neck on the line and really, really going for it. But what is your thinking from a polymer specialist lens?
Yeah, it's in terms of end of life, PHAs have some of the best outcomes. So I think until our society starts valuing the externalities of pollution, then it's going to be this chicken and egg of economics and scaling. But yeah, I think these PHA materials have great outcomes for when they are mismanaged, and I'm talking about litter situations, natural disasters. You know, anytime a brand is a little bit worried about finding their littering in an audit, consider PHA because I think it has the best end of life outcome for the mismanaged scenario where litters throw it on the side of the road or a natural disaster blows it out into the ocean. So all the other polyesters, I think that there's you know opportunities to design materials that will degrade like PHAs do in any environment. So I'm a polymer chemist, and that's part of the things that we've been studying is how to make materials degrade more quickly. And so there are strategies to design all those polyesters to degrade more rapidly, but also to preserve their you know to with some compromise, but preserve most of their processability.
Okay. Now I want to learn from you more on the usage side. So you've talked before and in your TED talk as well of multi-layered films. So one of the big challenges we as humankind face is like having these long shelf life packaging, and it has a very very stiff barrier requirement. You start your TEDx with a potato chip bag, and that's one of the most difficult, I would say. And you're talking about a water vapor barrier of less than 1 or even zero point 0.5 in that case,
Mm-hmm.
and an oxygen barrier of again similar under 1. So how, if you were to guide somebody looking at that product and making it compostable, as well as probably recyclable, because those films are not even recyclable. Um, what would you suggest the direction should be to find the right barrier levels? Because the customer doesn't compromise very easily, because and the logic is pretty strong, because they say, if my material gets harmed, think about the potato chip itself, then you're causing a bigger ecological disaster, because of the whole chain of how the potato was grown right through to getting packaged. So how do you see that evolving, so that again we can have materials that will degrade, recycle, and do the job of protecting what is inside?
Yeah, that's a loaded question, and I don't know if I know how to answer it, honestly. So, and I think it's because if consumers want to have all those things at low cost, there has to be something that's going to give, or the cost is going to go up. So I think it's a reasonable goal to go for something, a packaging format, try multi-layer packaging, the chip bag, that has maybe not the 0.5 grams of water per day, maybe it's one, and maybe the shelf life is less. And how much does that harm, sales of that product? That needs to be seen. But like, do we need to have such high packaging shelf life requirements, or can we bend a little bit on some of those performance metrics? Uh, the other side of the coin is innovation. So there's a lot of opportunity to innovate with those materials that recycling doesn't offer. And let me explain. When you have mixed materials and you have low mass, you don't have a recycling option anymore. So that I don't think that you can have something that's very lightweight and also mixed materials that's also recyclable, at least not economically recyclable. So I think that the opportunity in the compostable space is designing those higher performing materials and higher barrier, higher tensile strength, better heat seal materials using less material, because you can still have complexity in the packaging design if it's all compostable. You can't do that with recycling if you want it to be lightweight. So, when it comes to lightweightness and complexity, compostable is what you want to design for. It's much more challenging because now you got to think about 15 different polymers and additives and different grades, all these barrier requirements, metallization. It gets complex real quick, but you can actually technically do it if you want to design it to be compostable. I don't think you can technically design it to be recyclable and economically feasible.
So lots of the industry is looking at paper-based structures, and that's where my thought about recyclability comes in. Because again,
Mm-hmm.
paper will be recovered 70-80% compared to 7-8% for petroleum-based polymers. And they're looking at, and of course, I agree with you on the lightweighting. It probably
Mm-hmm.
won't be that kind of lightweight structure, but looking at a cellulosic structure, like a more dense, non-porous paper with some layers of different polymers. How do you see that becoming a reality in terms of really getting to be a structure which can replace a current? And we'll stay with the potato chip bag because that's probably the most complex. So how do
Yeah.
you do you see that happening? Do you see that structure evolving to both, in that case, recycling in the paper stream and
Mm-hmm.
completely degradable or compostable if strewn outside?
Yeah, I mean, I was thinking about it in the context of thermoplastics, not cellulosics. But if we want to keep the chip bag example, yeah, if we can get that barrier right, then that barrier is not going to come from the cellulosics. That's going to be the mechanical strength, right? Like that's it provides other functions. But the probably a thermoplastic, maybe a thermoset that's applied to that paper. If the recycling process, the alkali process, will destroy that chemistry and you can regenerate your fiber, great. And that can happen. Maybe not. I haven't seen the chip bag examples yet, but I've seen those types of formats in like less demanding packaging formats, like in paper mailers that need to have some water barrier. Amazon's already come out with several packaging formats that are like that. They have, I don't know what the coding is actually, but it is a recyclable format that's all paper and fiber based, and they've gotten rid of the plastic layers that are used in that packaging, but it does have some coating, which I presume doesn't present issues in recycling. But we're not trying to keep food shelf stable in that package for 2 years in a grocery store. So I think it depends on, it's going to be on a case by case scenario for the packaging format as to whether or not something like a multi-layer construct with paper or cellulosic products makes sense. I can think of plenty in the produce section, plenty of options where that would make sense for paper products. But if you go towards the center of the grocery stores, where you get the more shelf stable products, that's going to take a little bit more innovation, I think, before we can start to see paper and pulp products start to be in the center of the grocery stores. And as you know, and as I'm sure Packin knows, no paper is made the same.
No, man, it's the same as any other
Yeah,
polymer that you were talking about.
yeah.
PLA is not a PLA, and a PHA is not a PHA either. They all structures and molecular shapes and sizes and
Mm-hmm.
all of that. Okay, staying with the usages, the other one which I find fascinating is styrenes, and you mentioned them in between, and particularly when you can foam styrenes, so expanded polystyrenes, and it's been a great kind of structure when you look at, say, a foam cup. But the challenge again becomes it's whatever 96 to 98% air. Nobody is ever going to, you know,
Right.
downcycle it or whatever. Nobody's even going to collect it. It's going to float somewhere. How do you see more natural materials in the foaming side? Do you see a PLA being formed? I know that a lot of people are trying that. Do you think that we can make it stable enough that a foam cup can become? Because again, if you look at a paper cup structure, you're looking at a paper with a barrier layer and a ripple deck kind of outside. So there's multi-layer coming into a Starbucks cup. Instead of that, do you think there'll be a time when we could form a natural material and mimic uh, expanded polystyrene?
Yeah, I was at PAC-X this last November in Chicago, and I saw an example from a Korean company, and I'm drawing a blank for who they are right now. So, but they have a PHA foam that looks a lot like EPS. In a similar density, about 0.05, maybe a little bit higher. But yeah, I've seen some promises with foamed PHAs, and I think that was a CJ Bio based resin. I don't think the company that made the foam was it wasn't CJ Bio, but I've seen some advances in the foam space for PHAs. Yeah, I've also seen it for actually for paper products like conventional kind of cardstock for making cardboard packaging for insulated coolers, watertight insulated coolers. So actually the paper packaging space is starting to infiltrate into the EPS for the long term cold storage as well. So I've seen paper products invade that space as too. So there's a lot of opportunity to replace EPS because of its challenges to recycle and its environmental problems.
Yeah, no, for sure. Cellulose acetate is one of them
Mm-hmm.
that they've tried to foam, and
Oh yeah.
foam uses chitin and starches again, which exactly what you're talking about in the insulation side. So let's hope that that would take place too. One of the things that you mentioned in passing before is the law side of it, where they say if it's 90% degradable, it's
Mm-hmm.
okay. It'll be considered compostable or degradable. How do you see that? Do you think that that's kosher? That because many times we find our scientists saying that, oh well, it meets the norm, it meets the
Mm-hmm.
90% degradation norm, and is that a good argument that if it meets 90%, that's okay? We can expect that it'll be all right outside in nature, or do you see it differently?
Yeah. Good question. So the you're referencing the ASTM D6400, which is that defines the standards and the requirements for degradation. And Section 6 in that standard defines 90% biodegradation is required for a material to be considered a biodegradable plastic or a compostable plastic. Um, and the requirement of 90%, the reason why it's not 100%, really alludes to the precision of the analytical technique. So it's a biological experiment. It's systems biology, and everything's done in triplicate as a minimum. And that technique is only has a precision of about plus or minus 10%, um, for up to 6 months for the industrial composting standard. So the reason for that 90% is really about the precision of the testing, and not about the assumption of, oh well, 10% we can allow to not degrade. Um, but there is a provision for that, and that is right now I believe it's 1% right now, up to 5 chemistries or 5 additives. Each can be added up to 1% that are not compostable. So you can basically choose up to 5% by weight of your resin. You can put in whatever you want for compounds A, B, C, D, E, and F. And as long as the whole construct is biodegradable, or 90% of that material will mineralize, then that's considered a pass. And that's where the standard is being tolerant, to allow the industry to innovate. And it has to basically give a little bit, because if the requirement was absolutely none, then it would not be good for the industry, and because we wouldn't have solutions for that yet. So I think it's really fair, to have some allowable amount of non-degradable materials to be acceptable in the standards, because it's a space of innovation. We're 60 years behind the petrochemical industry in the space, so it's going to take some time to get to those idealized solutions.
And what do you think of the European standards, where they are looking at more of the polymer structure itself, right? They are saying that, was that nature derived, or was it similar to nature? It gets into the bioplastics that we were talking about, and they don't find that kosher. They say that, okay, if it's a PHA, I don't think PHA has made the list either. I'm not so sure, but celluloses are okay because they are found in nature.
Mm-hmm.
But many of the biopolymers are also not considered kosher. So, do you have an understanding of that? And what
Uh,
can you
I
kind of?
have an opinion of it, I suppose, but at the end of the day, I think what it comes down to is whether or not organisms know how to deconstruct those polymers, and whether or not they'll be persistent. I'm agnostic as to whether or not they're synthetic or made by biology, but I understand the caution that those agencies have around semi-synthetic polymers. We're toying around with the architecture of the backbones, and to give rise to new properties, and we don't know if it's going to be compostable. But I think what it requires for those claims that it's safe, that it's not going to be persistent, those are big claims that requires big evidence, and I think that's what might be lacking from some scientific endeavors. Respirometry is a great analytical tool to gather that evidence, but it's not the only tool. If you really want to have that claim, you should do some isotope work. And there are strategies to do stable isotope analytical testing that doesn't require, like, making molecules with C14, C13 labeled isotopes. So there are ways to prove metabolism, but I think that's what it takes. Is it's going to take a lot of proof. But that's my opinion. I think that they are cautious, but I think that I'm agnostic as to whether or not the material comes from nature or if it's made by man, as long as microorganisms know how to deconstruct it.
No, I think that's smart. But do you think we also hear of this whole news item that keeps coming up, that they have found a microbe that can ingest plastics?
Mm-hmm.
So do you think that's a possibility, or do you think we are creating more havoc by creating a microbe that will, eat into a polyethylene or something like that? So I know how much of that is just kind of media frenzy, and do you think there is something that might come out in that direction?
Yeah, it's like our industry is not immune to greenwashing, just like in the recycling industry. So as it grows, we have to be cautious of these kind of claims. And I've seen the mealworms eating polystyrene, and but there's a reason why we see no companies developing mealworm reactors to digest our styrene or polystyrene. It's not true. It doesn't. I have not seen the big evidence for those big claims.
And you talked about ingestibility, and that's a huge challenge, right? Because as humans, we are kind of damaging the rest of the planet. Today, again, going back to India, there won't be any stray cow or stray dog or stray pig that will not be found with kilos of plastic inside its
Right.
digestive organs. So when you look at toxicity and ideas around that, it's important that we create materials that will also, if ingested by marine life or animals, it is still all right. And when I talk to a lot of scientists, they're not even sure about PLA, that, what is the
Hmm.
damage that it does inside. And is that what you mean when you talk about the test that you were talking about just before the last question?
In the context of persistence, yeah, a little bit in terms of ingestion. So, so really, all plastics, I should say all plastics, but really most materials, I should say, will fragment as they degrade, whether that's a product of biological processes or abiotic processes. I mean, even inorganic chemistries will fragment with time. So disintegration, that process of fragmentation, is a natural process. What we want to do is ensure that disintegration goes all the way down to the molecule, and that the the molecules are being metabolized in some way, and you have to be able to prove that metabolism, which is not trivial. Respirometry, for instance, is an indirect technique of metabolism. It's not a direct measurement. Um, so, in the context of you know having those big claims for that big proof, that's what I meant from terms of microbes being able to consume that plastic. Um, and then remind me, what was the second part of that question? Sorry,
I
Vid.
mean that, if any animal or marine life
Yeah,
consumes it, how does it impact their digestive
right, right. Yeah, so I think it depends on the nature of what those animals are consuming. If the plastic is persistent, I've used this term before, persistent plastic. That means that in the environment it'll persist for years and years and decades, and it has the opportunity, the time, to absorb everything else that it's collecting on the oil slick. The density of a lot of those plastics is the same of petroleum and gas, and it resides on the surface of water, right where all those other nefarious compounds are, and they act as sponges and will absorb those small molecules over time. Uh, and then if you ingest that, or your farm animals ingest that's an opportunity for toxicity coming from that microplastic. Or if it's a large piece of plastic, it doesn't matter. But if it's a compostable material, it doesn't have the time. It can't persist in the environment. Then there's no opportunity to absorb, and uh, the material is basically gone over a course of months, hopefully shorter than years, but in the course of months. And basically, there's nothing left for the animals to ingest. So they can't be persistent. Now, do they fragment and make microplastics? Absolutely. They make nanoplastics? Yes. But the assumption and the understanding and really the evidence needs to be showed that that material will convert into biogas. And it's challenging to study things kind of between 5 microns and 5 angstroms. It's easy to look under a microscope down to a certain size, but with some of the techniques we're using, we're just looking at end products of like systems biology. So we do make some assumptions, once we can't see with the microscope.
Yeah, I've been listening to a podcast around chip making, and it's all down to 3 nanometers now. And, they're able to make those chips, which is amazing, right?
Mm-hmm.
So hopefully, slowly we'll be able to analyze materials at a much more micro, nano level, and learn from how nature works. And that takes me to the other area I wanted to actually explore with you. When we look at nature's chemistry, the fundamental building blocks seem to be sugars and proteins, amino acids, carbohydrates,
Mm-hmm.
and the periodic. If you look at the whole periodic table, the nature uses a very small part of it. So, how inspired are you by nature's mechanisms of creating packaging? And everything is wonderfully packaged, very apt, of course, grows with the product and goes down with the product, goes out with the product. So, is that something, is that an area that inspires you? And how do you see that? Is there a way we can really learn from nature's way of constructing things? And do you adapt any of it in your work?
Yeah, it's a really good question, and I do. Yeah, of course, I look at nature's synthetic pathways. I mentioned a little bit earlier the Krebs cycle, but if you can look at the some of the structures of metabolic pathways of biology, it gives some clues in terms of like what biology likes to do in terms of organizing its molecules for digestion. And there's actually a wealth of information in the literature about how enzymes operate on small molecules. So it's really about looking at how nature's machines work, the enzymes. It's all enzymatic chemistry, and I'm not going to pretend to know how to design the enzymes or how they ultimately function. But you can learn from the clues about what molecules they input and spit out, and the cycles that are involved in the biological processes. There's a reason why you don't see, you know, styrene in a lot of those biological processes, and it's not biodegradable because it's foreign to nature, at least the metabolism.
But are there inspirations in terms of packaging in nature? For example, I have a great inspiration. I don't know if you've ever seen it. It's the water spider. The water
Mm-hmm.
spider builds a web inside underwater, and it's, of course, a terrestrial being, but it creates it, and it's all amino acids. And it creates it so that it can diffuse air and it has enough barrier. It can procreate there. It can eat inside the web. So that's one of my inspirations. The other one is right in front of me. It's a pomegranate,
Mm-hmm.
the structure. Do you have any inspirations that you think, wow, how did nature create this substance? It's so beautifully structured. And, I want to
Yeah,
learn from your scientist's eye,
yeah,
like how
yeah.
do you see those structures?
So what you're talking about amino acids reminded me of some work I did on catechol chemistry. And so catechol it's just an oxidized tyrosine. You just add one more oxygen next to the alcohol that's present on tyrosine, you get catechol. And it's a common molecule that's used in one electron redox processes in nature. It's used in tree bark. It's used in all processes in our body that I don't fully understand. But it's also what's muscles, used to stick to rocks. It's the amino acid they secrete that oxidizes with air, and in basic environments like ocean water, will make very strong metal oxide bonds, and that's how they can survive the tidal forces. So that's how all those muscles will hold on in the strong seas, and so that's a bio-based glue that nature uses, and designing compostable glues. So you can kind of naturally see how there's some inspiration there. We don't use catechol in the glues that we're using, but there's a lot to be learned from some of those examples.
Yeah, I
Yeah.
can definitely see inspiration into your adhesive pursuit. That how nature does things. So it's an interesting. I was just like last week. I was in Chengdu in China,
Mm-hmm.
and we are engineering one large factory, and our engineers are in China. And I was telling them exactly what you were talking about in terms of enzymes, because Chengdu is full of pandas. And I said, guys, we are looking at this solvent kind of chemistry, which has always got harmful chemicals, like we are using sodium hydroxide and things like that. So how does the panda do it? Ultimately, it is digesting so much of bamboo.
Mm-hmm.
What is that enzyme? And of course, we've done a lot of work around, say, white trot mushrooms, and how they again degrade the trees, instead of using the sulfites and the sodium kind of processes. So yeah. So is there any, again, from looking at and nature always has water based chemistry, right? It's all
Mm-hmm.
green, so it's only solvent is water. And do you have any ideas around the enzyme side, in terms of nature and how we can alter the kind of chemistry we use in industry with inspiration from nature?
Yeah, I'm more so in. I like to study enzymes in terms of deconstructing polymers, more so than building them up. But I think when you think about what a what a biological reactor is it's constantly supplying like a new feedstock of enzymes as it's going through biological processes. But if you do that in the lab ex situ, ex vivo, it's going to be just you put the enzymes in, let them do their thing, and there's going to be a turnover that's going to present some challenges for it to be economically viable, perhaps. I'm just speculating. I don't do a lot of enzymatic chemistry in that regard. But I know, like, getting the yield up as much as possible, and enzymes aren't exactly a cheap material to make if you want to purify them. But I think about feedstocks that are really diverse, like waste feedstocks, like wastewater. A lot of available carbon sources, and if we can figure out, we, the scientific community, can figure out ways to use enzymes to purify those kind of feedstocks. That's where I think like you could tolerate the low yields, the low titers. So I think there's a lot of opportunity in the high volume waste industry, um, just because you know, take a page from the polyolefins. If you use a waste material, it's going to be cheaper.
No, and then just to clarify, it is deconstruction. Even in
Mm-hmm.
the case of, say, a pulping process,
Mm-hmm.
it is ultimately you're trying to separate the lignins and the celluloses and the hemicelluloses, and then that's the challenge with us as humans, right? Nature does additive manufacturing. We still do mostly subtractive manufacturing. So it's kind of
Yeah, it's true.
parsing it out and then putting it together and hydrolyzing it or whatever. So most of the work that the enzyme is still doing is to do with deconstruction. And it's interesting that you mentioned the wastewater side, and I've seen some remarkable work, especially using diatomic structures in enzymes, and seeing how nature does it and then utilizing it in treating the wastewater. So you're so right. Okay, we have to take this conversation towards closure.
Sure.
So are there what are the most exciting polymers for you, and the ones that you think that this is really going to create magic in the future? Name two, three of them which you think that these are things that I would really like to see scale.
So the first one that comes to mind is I have to come at it with my implicit bias. Is the technology we're trying to commercialize this year? We call it NMIG. G is for glue, but it's a home compostable adhesive, and it's great for fruit labels. It's great for stickers, but I can see how this polymer can be used in all kinds of other applications. Like I think this is going to be the use case that'll break it, get us into the industry and get a commercialized product. But I have to be confident with it, and we're going to develop a lot more technologies out of it than just some adhesives. So yeah, NMIG is what we call it. NMI for the New Materials Institute. G is for glue.
Still
Um,
not.
yeah, and then also I've been doing a lot of work with PBSA. I mentioned that earlier in the talk. It's a fully synthetic polyester, but it is low temperature compostable, so soil or home compost that will degrade, and it is a little bit more controllable than fermentation. And in terms of the polymer architecture, I'm not saying you can't control polymer architecture with fermentation. Uh, uh, we study this in our group as well, and but when it comes to fully synthetic uh, polymer, it's got good control over architecture, and also it has an established supply chain, so it's a commercially viable product right now, and it's kind of been a material of choice for studying multi-layer packaging. Yeah, so PBSA is on that list as well too. Um, and I also want to, in terms of the polyester starch blends, there's a lot that are out there. I think that there's a lot of opportunity too with the blends because I think it's not fully well understood or fully well characterized how those blends degrade. Their material properties are there. We know that they're compostable, and it seems like a lot of those thermoplastic starch blends will degrade at the low temperatures at 20 Celsius. Uh, it might take a year, but they will mineralize. So I think there's a lot of promise in the thermoplastic starch blends because you get different properties out of those polyester blends with the starches. So that's kind of where I would stand in terms of if I had to choose three. Um, but
You can choose more.
there,
Nothing stops you from choosing more.
right,
If there
right.
is more that comes to your mind, or more that come to your mind.
Well, I'd like to also look more into the polyurethanes, just as a class of materials. I think that it's kind of underexplored for compostability, and the reason why I mentioned that too, in the context of this podcast, is for cellulosic coatings. So polyurethanes are used in all kinds of coatings, and they're very durable and provide a lot of good barrier properties. I think there's a lot of opportunities because of the flexibility of that platform. So a lot of opportunities, I believe, with polyurethanes too, from a synthetic standpoint.
Superb. Since you're in this environment of being surrounded by young minds in the university and that area, how do you see the industry? How should the industry attract more and more new, talent to come into the space of sustainable packaging? Do you see a lot of young minds interested, or should the industry be doing more in order to bring more youngsters into the mix? Because that is what is going to create big change.
Oh man, that's a loaded question. I think HR would be better answered. But yeah, I think I don't have a good answer for you. I think you got me stumped with this last one, but I think we just need a little bit more optimism from our, I guess, our funding agencies around compostable materials. I think it starts with the research projects because that's what gets the students involved and gets them interested and excited. And those research projects come from funding sources like national sources that typically have focused, at least in the United States, more on recycling than on composting, and the efforts of sustainability. And I know there's a history there for that, so that's fine. But I think that having a good look at the funding structure from a national or state level would be something to look at in terms of a high level of importance for engaging students, because that's what gives rise to those projects, and that's what gives rise to educating the new scientists, the new engineers that will develop these materials.
Superb.
Yeah,
So just the second to last. One of the big challenges that we face as an industry is the idea of scale. So of course, there is going to be in your talk, 8.3 billion is the number you mentioned. I think
yeah.
tons of plastic that is going to be created in another 3, 4, 5 years, and so that's a huge number. And how do you see us as compostable packaging manufacturers going towards that scale? And do you see that is going to happen? And what keeps you optimistic around scale?
Yeah, it's it, I'll follow it up with a question that was asked to me some years ago by one of my committee members in my defense. Um, if every material was bio-based, where would you grow the food? It's a simple question, but if you look at the scale of things, it's a serious question to ask. And what kind of keeps me optimistic is that in the context of our industry, compostable packaging, the organisms don't really care if it's bio-based or not. I think it's something we need to obviously we need to work towards, but I think what keeps me optimistic is that we can still use petroleum feedstocks to keep the cost and low and help grow the scale. So it's going to help. We need that industry as much as we might want to change it, but we need that industry to help support and grow this one. So I think that there's uh, you know, leveraging the economy of scales of the petroleum industry is going to help grow the compostables industry from a synthetic polymer chemistry standpoint. Maybe not the same case for fermented materials, but yeah, I think there's some optimism there for the economy of scale.
Yeah, and also I interviewed a couple of weeks back Molly Morse. I don't know if you know her, but she's creating a lot of PHA from methane. So that's
Yeah.
very interesting as well, right? So you
Hmm.
can get methane from numerous sources. You don't need
Plenty of landfills around.
plenty of landfills around. Exactly.
Yeah.
Uh, so that's so of course this takes me to my final question, and I'm very excited to hear your answer. What does good garbage mean to you?
Yeah. Yeah. So I think good garbage is garbage that is cost savings. It doesn't sound very sexy, I know, but every dollar saved is a dollar earned in government, and our governments are the people that deal with our garbage by and large. We have private haulers too, but I think good garbage is garbage that is not costly. So cost reducing garbage is good garbage. You could call it profitable garbage if you want, but it just depends on who you're asking. But I think that there are ways to make certain waste streams into a value added product, like food scraps. It doesn't have to be waste, and uh, obviously anything we keep out of the landfill is good.
I would not have expected that answer from you, Evan. So thank you for that. I was thinking it's going to be a more geeky answer on degradation or something like that.
Uh,
The economist in you kind of rose up and talked about cost and,
yeah,
and
you always have to consider that variable. But yeah,
agree.
that's
Yeah.
yeah,
So great,
it's been a
Evan. This has
pleasure.
been such a joy to have you and to learn from you. You know, the amount of ideas in terms of chemistry and polymers, it's just remarkable. And the work that you're doing is, again, something that humanity needs. So thank you so much for your work. Thank you for agreeing to be on the show. And thank you for the conversation.
Yeah, thank you so much, Ved, for the opportunity and the work you're doing here with this communication is paramount because we need people like you to communicate these stories. Otherwise, we're just operating in a vacuum. So, thank you.